Imagine you're writing your address on an envelope. You'd probably write your street, your city, maybe your country. But what if we kept going? What if we wrote our complete cosmic address, pinpointing exactly where we are in the vastness of space? Today, we're beginning an extraordinary journey that will take us from the ground beneath our feet to the edges of our solar system. And in doing so, we'll start to grasp just how vast our universe truly is. Let's start with Earth, our home, a blue marble spinning through space at over 1,600 kilometers per hour at the equator, though we don't feel it. From space, Earth is breathtakingly beautiful, a world of swirling white clouds, deep blue oceans covering 71% of its surface, and continents painted in browns and greens. It's the only place in the entire universe where we know, with absolute certainty, that life exists. Earth is approximately 12,742 kilometers in diameter, large enough that you could fit about 49 moons inside it if it were hollow. But in cosmic terms, Earth is tiny. It's the third planet from our sun, sitting in what scientists call the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist on its surface. This perfect positioning, combined with our protective atmosphere and magnetic field, makes Earth the oasis of life that it is. But Earth doesn't travel alone. Orbiting us at an average distance of 384,400 kilometers is the Moon, our only natural satellite and the brightest object in our night sky after the sun. The Moon is tidally locked to Earth, meaning the same side always faces us. It takes about 27.3 days to complete one orbit around our planet, and its gravitational pull creates the tides in our oceans, a phenomenon that has shaped life on Earth for billions of years. The Moon is roughly 1/4 the size of Earth, making it unusually large relative to its parent planet. In fact, the Earth-Moon system is sometimes considered a double planet rather than a planet and satellite. Standing on the Moon and looking back at Earth, you'd see our world hanging in the blackness of space, about 4 times larger than the Moon appears to us, glowing with that distinctive blue hue. Now, let's zoom out further. Earth is part of the inner solar system, home to 4 rocky planets: Mercury, Venus, Earth, and Mars. These terrestrial planets all share similar characteristics. They're relatively small, dense, and have solid surfaces you could theoretically stand on. Mercury, the closest planet to the Sun, is a scorched world of extremes, where temperatures swing from 430 degrees Celsius during the day to minus 180 degrees at night. Venus, often called Earth's twin because of its similar size, is actually a hellish world shrouded in thick clouds of sulfuric acid, with surface temperatures hot enough to melt lead due to a runaway greenhouse effect. Then there's Mars, the red planet, sitting about 228 million kilometers from the Sun. Mars is cold, dusty, and has a thin atmosphere, but it once had flowing water on its surface. Today, it's the focus of intense scientific study as we search for signs of past life and contemplate humanity's future as a multi-planetary species. Between Mars and the outer planets lies the asteroid belt, a region filled with millions of rocky objects ranging from tiny pebbles to Ceres, a dwarf planet nearly 1,000 kilometers across. Despite how it's depicted in movies, the asteroid belt isn't densely packed. You could fly through it and likely never see an asteroid with your naked eye. These are the leftover building blocks of our solar system, prevented from forming into a planet by Jupiter's massive gravitational influence. Beyond the asteroid belt, we enter the realm of the gas giants. First comes Jupiter, the king of planets, so massive that all the other planets in our solar system could fit inside it. Jupiter is 778 million kilometers from the Sun and has at least 95 known moons, including Ganymede, the largest moon in our solar system. which is even bigger than Mercury. Then there's Saturn, famous for its stunning ring system made of countless particles of ice and rock, some as small as grains of sand, others as large as houses. Saturn sits about 1.4 billion kilometers from the Sun. So far that sunlight takes over an hour to reach it. Further out, at 2.9 billion kilometers, we find Uranus, an ice giant tipped on its side, likely due to a massive collision early in its history. And finally, Neptune, the windiest planet in our solar system, orbits at about 4.5 billion kilometers from the Sun, where temperatures plunge to minus 200 degrees Celsius. But our solar system doesn't end with Neptune. Beyond it lies the Kuiper Belt, a region of icy bodies that extends from about 30 to 55 astronomical units from the Sun. An astronomical unit, or AU, is the distance from Earth to the Sun, about 150 million kilometers. This is where we find Pluto, the famous dwarf planet that was reclassified in 2006, along with thousands of other icy objects. The Kuiper Belt is like a frozen archive of the early solar system. These objects have remained largely unchanged for over 4 billion years, preserving clues about how our cosmic neighborhood formed. It's also the source of many short-period comets, those beautiful visitors that occasionally grace our skies with their glowing tails. Finally, we reach the Oort Cloud, the true outer boundary of our solar system's gravitational influence. This is a theoretical spherical shell of icy objects that surrounds our solar system at distances between 2,000 and 100,000 astronomical units from the Sun. To put that in perspective, the Oort Cloud extends nearly halfway to the nearest star beyond our Sun. No spacecraft has ever reached the Oort Cloud, and none will for thousands of years. Voyager 1, humanity's most distant spacecraft, launched in 1977, is currently about 160 Australian dollars from the Sun and won't reach the inner edge of the Oort Cloud for another 300 years. It won't emerge from the outer edge for another 30,000 years. The Oort Cloud is thought to contain billions, perhaps trillions, of icy objects. It's the source of long-period comets, those rare visitors that take hundreds or thousands of years to complete a single orbit around the Sun. When gravitational disturbances nudge these objects toward the inner solar system, they become the spectacular comets that have awed humanity throughout history. Let's take a moment to truly appreciate the scale we've just traversed. If we shrunk the Sun down to the size of basketball, Earth would be about the size of a peppercorn located 26 meters away. Neptune would be a small marble over 800 meters distant. And the Oort Cloud? It would extend for nearly 23 kilometers in every direction. Now that we've explored our solar system, it's time to venture far beyond its boundaries and discover the vast stellar island we call home, the Milky Way galaxy. On a clear, dark night, away from city lights, you can see a luminous band stretching across the sky, a river of light that ancient civilizations wove into their myths and legends. What you're seeing is actually our view from inside the galaxy itself, looking through the disk of billions of stars that make up our cosmic home. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure with spiral arms extending outward like a cosmic pinwheel. If you could view it from above, it would look like a magnificent spiral with glowing arms swirling around a bright central bulge. The galaxy is absolutely enormous, approximately 100,000 to 200,000 light years in diameter. To put that in perspective, light traveling at 300,000 kilometers per second would take 100,000 years to cross from one side of the galaxy to the other. Our galaxy contains between 100 billion and 400 billion stars. That's right, hundreds of billions of suns, each potentially hosting their own system of planets. Some of these stars are ancient red giants nearing the end of their lives. Others are newborn blue giants burning hot and bright, and countless others are middle-aged yellow stars like our own Sunday. The sheer number is difficult to comprehend. If you try to count every star in the Milky Way at a rate of 1 per second, it would take you over 10,000 years to finish counting. But stars aren't the only inhabitants of our galaxy. The Milky Way also contains vast clouds of gas and dust called nebulae, where new stars are born. These stellar nurseries are some of the most beautiful objects in space. Glowing regions of ionized hydrogen, dark clouds silhouetted against star fields, and turbulent regions where gravity is pulling matter together to create the next generation of stars. The galaxy also hosts hundreds of globular clusters, dense spherical collections of hundreds of thousands of old stars that orbit the galactic center like satellites. Let's talk about the structure of our galaxy in more detail. The Milky Way has several distinct components. At the center is the galactic bulge, a dense, roughly spherical region packed with older, yellowish stars. This central bulge is about 10,000 light-years across and contains some of the galaxy's oldest stellar populations. Extending from the bulge is a bar-shaped structure about 27,000 light-years long, made up of stars and gas. This bar rotates as a single unit and plays a crucial role in funneling gas toward the galactic center, triggering star formation. Spiraling outward from this central bar are the galaxy's arms, long, winding structures where stars, gas, and dust concentrate. The Milky Way has 4 major spiral arms: the Perseus arm, the Scutum Centaurus arm, the Norma arm, and the Sagittarius arm. These aren't rigid structures like the spokes of a wheel. Instead, they're density waves, regions where stars and gas bunch up temporarily as they orbit the galactic center. Think of them like a cosmic traffic jam where cars slow down, creating a denser region, then speed up again as they move through. Our solar system resides in a minor arm called the Orion Spur or Local Spur, which connects the Sagittarius and Perseus arms. We're located about 26,000 light-years from the galactic center, roughly halfway out from the center to the edge in what you might call the galactic suburbs. This position is actually quite fortunate for life. Closer to the center, there's more radiation, more frequent supernovae, and gravitational disturbances that could disrupt planetary systems. Too far out, and there wouldn't be enough heavy elements to form rocky planets like Earth. Our entire solar system orbits the galactic center at a speed of about 828,000 kilometers per hour. Even at this tremendous velocity, it takes approximately 225 to 250 million years to complete one orbit, a period sometimes called a galactic year. The last time our solar system was in its current position relative to the galaxy, dinosaurs were just beginning to emerge on Earth. Since our planet formed 4.5 billion years ago, we've completed only about 20 orbits around the galaxy. At the very heart of the Milky Way lies something extraordinary and terrifying: a supermassive black hole called Sagittarius A*, pronounced Sagittarius A star. This cosmic monster has a mass equivalent to about 4 million suns, all compressed into a region smaller than our solar system. Despite its enormous mass, we can't see it directly because it's a black hole. Nothing, not even light, can escape its gravitational pull once it crosses the event horizon. However, we can observe Sagittarius A* by watching how it affects nearby objects. Astronomers have tracked stars orbiting incredibly close to the black hole, moving at speeds up to 8,000 kilometers per second, about 3% the speed of light. These observations have provided some of the strongest evidence for the existence of supermassive black holes. In 2022, scientists released the first ever image of Sagittarius A*, captured by the Event Horizon Telescope, a network of radio telescopes spread across the entire planet working together as one massive instrument. The region around our galactic center is far from quiet. It's a chaotic environment filled with intense radiation, powerful magnetic fields, and energetic processes. Giant molecular clouds orbit the black hole, occasionally getting torn apart by its gravity. Star formation happens at a frantic pace, and massive stars live fast and die young, exploding as supernovae and enriching the surrounding space with heavy elements. Surrounding the visible disk of the Milky Way is the galactic halo, a roughly spherical region extending perhaps 130,000 light-years from the center. This halo contains globular clusters, streams of stars from smaller galaxies that our Milky Way has consumed over billions of years, and something else, something we can't see but know must be there. This invisible component is called dark matter, mysterious stuff that doesn't emit, absorb, or reflect light, but reveals its presence through gravitational effects. In fact, the visible matter in the Milky Way, all those billions of stars, all the gas and dust, everything we can see, makes up only about 15% of the galaxy's total mass. The remaining 85% is dark matter, forming an enormous invisible halo that extends far beyond the visible edge of the galaxy. We know it's there because the outer stars in our galaxy orbit far too quickly to be held in place by the gravity of visible matter alone. Without dark matter's additional gravitational pull, those stars should fly off into intergalactic space, yet they remain bound to the galaxy. Having explored our home galaxy, it's time to pull back our perspective even further and discover that the Milky Way doesn't exist in isolation. Just as stars cluster together to form galaxies, galaxies themselves gather into groups and clusters, bound together by gravity across millions of light-years of space. Our galactic neighborhood is called the local group, and it's a collection of more than 80 galaxies spanning roughly 10 million light-years across. The local group is dominated by 3 large spiral galaxies. The Milky Way is one, and the other 2 are the Andromeda Galaxy and the Triangulum Galaxy. These 3 giants contain the vast majority of the local group's mass and stars, while dozens of smaller dwarf galaxies orbit around them like cosmic satellites. Let's start with our closest major neighbor, the Andromeda Galaxy, also known as M31. Andromeda is the most distant object visible to the naked eye from Earth. On a dark, moonless night, away from light pollution, you can see it as a faint, fuzzy patch in the constellation Andromeda. What you're seeing is light that left that galaxy 2.5 million years ago, when our ancestors were just beginning to use stone tools. Andromeda is magnificent, a spiral galaxy similar in structure to the Milky Way, but significantly larger. It contains approximately 1 trillion stars, more than twice as many as our galaxy, and spans about 220,000 light-years in diameter. If Andromeda were brighter in our sky, it would appear 6 times wider than the full moon, an absolutely spectacular sight. Like the Milky Way, Andromeda has a supermassive black hole at its center, though this one is even more massive, weighing in at around 100 million solar masses. Andromeda isn't stationary relative to us. It's actually moving toward the Milky Way at about 110 kilometers per second. This might sound alarming, but remember, space is vast. The collision won't happen for another 4.5 billion years, giving life on Earth plenty of time to evolve, thrive, and perhaps even spread to other star systems before the merger begins. The third major member of our local group is the Triangulum Galaxy, or M33, located about 2.7 million light-years away. Triangulum is smaller than both the Milky Way and Andromeda, containing only about 40 billion stars, but it's still an impressive spiral galaxy in its own right. Under excellent conditions, Triangulum can be seen with the naked eye, making it one of the most distant permanent objects visible without a telescope. This galaxy is also moving through space, and it may eventually be captured by Andromeda's gravity or possibly collide with the Milky Way in the distant future. Beyond these three giants, the local group is populated by dozens of dwarf galaxies. These smaller galaxies come in various types: dwarf spheroidals, dwarf ellipticals, and dwarf irregulars. Despite their diminutive sizes, containing anywhere from a few million to a few billion stars, they're crucial members of our galactic neighborhood and provide valuable insights into galaxy formation and evolution. The Milky Way has its own retinue of satellite galaxies. The most famous are the Large and Small Magellanic Clouds, visible from the southern hemisphere as bright, cloudy patches in the night sky. These irregular dwarf galaxies orbit the Milky Way and have been gravitationally interacting with our galaxy for billions of years. The Large Magellanic Cloud, at about 160,000 light-years away, contains roughly 30 billion stars, while the Small Magellanic Cloud, slightly more distant, has around 3 billion stars. Other notable Milky Way satellites include the Sagittarius Dwarf Elliptical Galaxy, which is currently being torn apart by our galaxy's tidal forces, and the Canis Major Dwarf Galaxy, which may be the closest neighboring galaxy to our own, though astronomers debate whether it's truly a separate galaxy or just part of the Milky Way itself. Andromeda also has its family of satellite galaxies. M32 and M110 are two dwarf elliptical galaxies that orbit Andromeda, visible in the same telescopic field of view as their giant parent. Andromeda may have consumed and absorbed many smaller galaxies throughout its history, and evidence of these ancient mergers can still be seen in stellar streams and unusual structures within a galaxy. What's particularly fascinating about the local group is that it gives us a laboratory for studying galaxy interactions and evolution. We can observe galaxies at various stages of merging, from the early stages of gravitational interaction to complete absorption. We can study how galaxies exchange gas, trigger star formation in each other, and how supermassive black holes interact when their host galaxies collide. The local group also represents the boundary of what we might call our cosmic home territory. Every galaxy in the local group is gravitationally bound to the others. They're part of our cosmic family, destined to remain together even as the universe expands and most other galaxies recede from us. In the far future, billions of years from now, when cosmic expansion has carried distant galaxies beyond our observable horizon, the merged remnant of our local group will be the only galaxy visible in the sky, a lonely island in an expanding cosmic ocean. Understanding the local group also helps us grasp the hierarchical nature of cosmic structure. Just as planets orbit stars and stars orbit galactic centers, galaxies group together under mutual gravitational attraction. The local group itself is just one small part of an even larger structure, the Virgo supercluster, which we'll explore soon. This nested hierarchy of structures extends from the smallest scales all the way up to the largest features in the observable universe. From our vantage point on Earth, we're residents of a planet orbiting a star in a galaxy within a group of galaxies. Each level of this cosmic address reveals new wonders and raises profound questions about our place in the universe. Galaxy clusters and superclusters, cosmic cities. As we continue our journey outward, we discover that galaxy groups like our local group are just the beginning. On even larger scales, the universe organizes itself into magnificent structures called galaxy clusters and superclusters. Cosmic cities containing thousands of galaxies bound together by gravity across tens or even hundreds of millions of light years. Galaxy clusters are among the largest gravitationally bound structures in the universe. While our local group contains about 80 galaxies, a typical galaxy cluster can contain anywhere from hundreds to thousands of galaxies, all swirling together in a cosmic dance that has lasted billions of years. These clusters are not just collections of galaxies. They're vast ecosystems filled with hot gas, mysterious dark matter, and dynamic processes that shape the galaxies within them. Let's begin with the Virgo cluster, the nearest major galaxy cluster to us, located about 65 million light-years away in the direction of the constellation Virgo. The Virgo cluster is enormous, containing around 1,300 to 2,000 galaxies spread across a region roughly 15 million light-years in diameter. At its heart sits M87, a giant elliptical galaxy that made headlines in 2019 when scientists released the first-ever image of a black hole, the supermassive monster at M87 center, weighing in at 6.5 billion solar masses. The Virgo cluster dominates our cosmic neighborhood. Its immense gravitational pull affects everything around it, including our own local group. We're falling toward the Virgo cluster at about 400 kilometers per second, though we'll never actually reach it because the expansion of space itself is carrying us apart faster than we're falling together. This gravitational influence extends throughout what astronomers call the Virgo supercluster, a massive structure containing our local group and many other galaxy groups, all influenced by Virgo's gravity. Even more impressive than Virgo is the Coma cluster, located about 320 million light-years away. The Coma cluster contains over 1,000 identified galaxies, and possibly many more smaller ones we haven't yet detected. What makes Coma particularly important is that it was one of the first places where astronomers realized something was wrong with our understanding of the universe. In the 1930s, Swiss astronomer Fritz Zwicky measured the velocities of galaxies in the Coma cluster and found they were moving far too fast. By all rights, their speed should tear the cluster apart, sending galaxies flying off into space. The fact that the cluster remained intact meant there had to be much more mass present than we could see. Zwicky called this unseen mass dark matter, and his discovery would revolutionize our understanding of the cosmos. Today we know that galaxy clusters are dominated by dark matter. The mysterious, invisible substance makes up about 85% of the cluster's total mass. Another 10 to 15% consists of hot gas that fills the space between galaxies, heated to tens of millions of degrees by the cluster's gravitational pull. This gas is so hot it glows in X-rays, allowing us to map cluster structure using X-ray telescopes. The galaxies themselves, despite being the only visible components, account for less than 5% of the cluster's total mass. The environment within galaxy clusters is harsh and dynamic. Galaxies don't just orbit peacefully. They collide, merge, and interact in complex ways. When galaxies move through the hot intracluster gas, the gas pressure strips away their own gas reserves in a process called ram pressure stripping, shutting down star formation and gradually transforming spiral galaxies into elliptical ones. This is why galaxy clusters tend to be dominated by elliptical and lenticular galaxies rather than the gas-rich spirals common in less dense environments like our local group. Galaxy clusters themselves aren't uniformly distributed across the universe. They gather into even larger structures called superclusters, vast collections of galaxy clusters and groups stretching across hundreds of millions of light years. For decades, astronomers believed our local group was part of the Virgo supercluster, a structure containing the Virgo cluster and dozens of smaller groups, including our own. However, in 2014, astronomers redefined our cosmic address, using new methods to map how galaxies move through space. They discovered that we're actually part of an even larger structure called the Laniakea supercluster. The name Laniakea comes from Hawaiian words meaning immeasurable heaven, and it's an apt description. Laniakea contains about 100,000 galaxies spread across 520 million light-years. Our entire local group, the Virgo cluster, and dozens of other galaxy clusters all belong to this enormous structure. What defines Laniakea isn't just proximity, it's gravitational flow. All the galaxies within Laniakea are being pulled toward a single point called the Great Attractor, a region of space so dense with matter that it warps the motion of everything within hundreds of millions of light-years. The Great Attractor itself lies beyond the Milky Way's galactic plane, hidden behind dust and stars, making it difficult to observe directly. But its gravitational influence is undeniable, pulling our local group and countless other galaxies toward it at hundreds of kilometers per second. Beyond Laniakea, the universe contains numerous other superclusters, each a vast collection of galaxy clusters with their own gravitational flows and structures. The Shapley supercluster, located about 650 million light-years away, is one of the largest concentrations of galaxies in our cosmic neighborhood, containing more than 8,000 galaxies and exerting its own gravitational pull on surrounding space. These superclusters represent some of the largest structures in the universe that are actually held together by gravity. On larger scales still, cosmic expansion dominates, and structures are no longer gravitationally bound. The universe becomes a vast web of superclusters, connected by filaments and separated by enormous voids, a cosmic structure we'll explore in our next chapter. Understanding galaxy clusters and superclusters helps us comprehend how structure formed in the universe. These massive collections of galaxies didn't appear suddenly. They grew over billions of years as gravity pulled matter together, starting from tiny density fluctuations in the early universe and gradually building into the magnificent cosmic cities we observe today. As we zoom out to truly cosmic scales, something extraordinary emerges, a pattern so vast and intricate that it wasn't fully recognized until astronomers could map millions of galaxies across billions of light-years of space. The universe, on its largest scales, resembles a three-dimensional spiderweb, with galaxy superclusters strung along immense filaments of matter, surrounding enormous empty regions called voids. This is the cosmic web, the largest known structure in the universe, and it reveals the fundamental architecture of everything that exists. Imagine taking all the galaxies in the observable universe and plotting their positions in three-dimensional space. What you'd see isn't a random scattering of points, nor an even distribution. Instead, you'd observe a spectacular foam-like structure, walls and filaments of galaxies surrounding vast bubble-like voids. This pattern extends as far as we can see, repeating across billions of light-years, suggesting it's a fundamental feature of the universe itself. The filaments are the defining feature of the cosmic web. These are massive structures, hundreds of millions of light-years long and tens of millions of light-years wide, containing countless galaxies, galaxy groups, and galaxy clusters strung together like beads on cosmic strings. The filaments aren't solid structures. They're concentrations of dark matter, gas, and galaxies, regions where matter has accumulated over billions of years under the influence of gravity. One of the most famous filaments is the Sloan Great Wall, discovered in 2003. This enormous structure stretches across 1.4 billion light-years of space and contains hundreds of thousands of galaxies. It's so large that light takes over 1 billion years to travel from one end to the other. Yet even this immense structure is just one thread in the cosmic web, one of countless similar filaments weaving through the universe. But perhaps even more striking than the filaments are the voids, vast regions of space containing very few galaxies. These cosmic voids are truly empty on scales that defy imagination. The typical void is 100 to 400 million light-years across, though some supervoids can exceed 1 billion light-years in diameter. Within these regions, galaxy density drops to less than 10% of the universe's average. Some voids contain almost nothing at all, just a handful of small galaxies scattered across hundreds of millions of light-years of nearly empty space. The Boötes void, discovered in 1981, is one of the most famous examples. This nearly spherical region, roughly 330 million light-years in diameter, contains only about 60 galaxies where we would expect to find around 2,000. Standing in a galaxy within such a void, the night sky would be profoundly different from ours. Instead of seeing neighboring galaxies in every direction, you'd see darkness in most directions, with the nearest significant concentrations of galaxies impossibly distant on the horizon. How did this cosmic web form? The answer lies in the early universe, just after the Big Bang. When the universe was very young, matter wasn't perfectly smooth. There were tiny density variations, regions where matter was slightly more or less concentrated than average. These variations were incredibly small, less than 1 part in 100,000, but they were enough. In regions that were slightly denser, gravity pulled in more matter, making them denser still. In regions that were slightly less dense, matter flowed away toward the denser regions, making them emptier. Over billions of years, this process amplified. Dense regions grew denser, eventually forming the filaments and clusters we see today. Underdense regions became increasingly empty, evolving into the voids. Dark matter played a crucial role in this process. Because dark matter only interacts through gravity and doesn't collide with itself or emit radiation, it could collapse more efficiently than ordinary matter, forming the gravitational scaffolding along which galaxies would later form. Computer simulations of cosmic structure formation beautifully reproduce the cosmic web we observe. Scientists input the known properties of the universe, the amount of dark matter, dark energy, and ordinary matter, plus the tiny density fluctuations observed in the cosmic microwave background, and let gravity do its work over billions of simulated years. The result is a stunning match to reality, a universe filled with filaments, clusters, and voids arranged in an intricate web-like pattern. Where filaments intersect, we find the richest galaxy clusters, cosmic metropolises where thousands of galaxies congregate. These nodes in the cosmic web are sites of intense activity, galaxies colliding and merging, hot gas glowing in X-rays, and supermassive black holes growing as they consume surrounding matter. The Laniakea supercluster we discussed earlier is one such concentration, a knot in the cosmic web where multiple filaments converge. The cosmic web isn't static. It's evolving, driven by two competing forces, gravity pulling matter together and the expansion of space pushing everything apart. For the first several billion years of cosmic history, gravity dominated on these large scales, causing filaments to grow denser and voids to expand. But about 5 billion years ago, something changed. The expansion of space began accelerating, driven by dark energy, the mysterious force that makes up about 68% of the universe's total energy. Since then, cosmic expansion has been winning the battle. Voids are expanding faster than gravity can pull matter into filaments. Galaxy clusters that aren't already gravitationally bound are being carried apart by expanding space. In the far future, billions of years from now, this process will continue until galaxy clusters become isolated islands, separated by ever-growing voids, eventually losing sight of each other entirely as they recede beyond each other's cosmic horizons. The cosmic web also acts as a highway system for matter. Gas flows along filaments, channeling material from voids toward galaxies and galaxy clusters. This accretion of matter along filaments feeds galaxy growth and star formation. When we observe distant galaxies, we sometimes see long streams of hydrogen gas extending from the galaxy along filament directions, fuel being delivered along cosmic highways to sustain star formation. The observable universe, our cosmic horizon. We've journeyed outward from Earth through our solar system, our galaxy, our local neighborhood of galaxies, vast clusters, superclusters, and the cosmic web itself. Now we arrive at the ultimate frontier, the edge of everything we can possibly see. This is the observable universe, a sphere of space centered on Earth, beyond which light has not had enough time to reach us since the universe began. It represents both the extent of our knowledge and a humbling reminder of our cosmic limitations. The observable universe is approximately 93 billion light-years in diameter. Let that number sink in for a moment. If you could somehow travel at the speed of light, it would take you 93 billion years to cross from one edge to the other. Yet the universe is only about 13.8 billion years old. How can the observable universe be larger than the distance light could travel in the age of the universe? The answer lies in the expansion of space itself. When we look at distant galaxies, we're not just seeing them as they are now. We're seeing them as they were in the past because their light has taken time to reach us. A galaxy 1 billion light-years away appears to us as it was 1 billion years ago. The farther we look into space, the further back in time we're seeing. This means that our most powerful telescopes are also time machines, allowing us to observe the universe at different stages of its evolution. But space itself has been expanding throughout the entire time that light has been traveling toward us. Consider a galaxy that emitted light toward Earth when the universe was very young. That light began traveling through space, but while it was in transit, the space between us and that galaxy was expanding, stretching the distance the light had to cover. By the time the light finally reaches us billions of years later, that galaxy is much farther away than it was when it emitted the light we're now seeing. This is why the observable universe can be larger than 13.8 billion light-years across. Space has been expanding while light has been traveling. The most distant objects we can see are located about 46.5 billion light-years away from us right now, though they were much closer when they emitted the light we're currently receiving. These incredibly distant galaxies appear to us as they were more than 13 billion years ago, when the universe was less than 1 billion years old, young, chaotic, and very different from the universe we observe nearby. These early galaxies were smaller and less organized than modern galaxies. They were undergoing intense bursts of star formation, creating massive blue stars at rates hundreds of times faster than galaxies today. Many were colliding and merging, gradually building up the larger galaxies we see in the more recent universe. Observing these distant, ancient galaxies helps us understand how galaxies evolved over cosmic time, how the first stars formed, and how the universe transformed from a hot, dense state into the structured cosmos we inhabit. But there's a limit to how far back we can see with ordinary telescopes. About 380,000 years after the Big Bang, the universe underwent a crucial transition. Before this moment, The universe was so hot and dense that it was opaque. Light couldn't travel freely because it was constantly absorbed and re-emitted by free electrons. Then, as the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms. Suddenly, light could travel freely through space. The universe became transparent. This moment of transition left behind a glow that fills the entire universe. The cosmic microwave background radiation, or CMB. This is the oldest light in the universe, the afterglow of the Big Bang itself, and it represents the farthest we can see with electromagnetic radiation. The CMB appears to come from a distance of about 46 billion light years away and forms a spherical shell surrounding us in all directions, our ultimate cosmic horizon. When we observe the CMB with specialized telescopes, we're seeing the universe as it was 380,000 years after the Big Bang, when it was only about 3,000 Kelvin, cool enough for atoms to form, but still far hotter than the surface of the sun. Back then, this radiation was primarily visible in infrared light. But as the universe expanded over billions of years, this light was stretched to longer and longer wavelengths. Today, 13.8 billion years later, it appears primarily as microwave radiation, cooled to just 2.7 degrees above absolute zero. The cosmic microwave background isn't perfectly smooth. It contains tiny temperature variations, some regions slightly warmer, others slightly cooler by about 1 part in 100,000. These fluctuations are incredibly important because they represent the seeds of all cosmic structure. The slightly denser regions would eventually grow into galaxy clusters and superclusters, while the less dense regions would become voids. By studying the pattern of these fluctuations, scientists can learn about the fundamental properties of the universe, its age, composition, geometry, and fate. The CMB has been mapped with exquisite precision by satellites like COBE, WMAP, and Planck. These maps reveal not just temperature variations, but also contain information about the universe's composition. From these observations, we've learned that ordinary matter, the atoms that make up stars, planets, and ourselves, constitutes only about 5% of the universe's total energy. About 27% is dark matter, and roughly 68% is dark energy, the mysterious force driving the accelerating expansion of space. Beyond the cosmic microwave background, we cannot see with light. The early universe before recombination was opaque to electromagnetic radiation. However, this doesn't mean we're entirely blind to earlier times. Neutrinos, ghostly particles that barely interact with matter, were able to travel freely even in the very early universe. In principle, a cosmic neutrino background exists, though detecting it remains beyond our current technology. Similarly, gravitational waves from the early universe might carry information from even earlier times, possibly from fractions of a second after the Big Bang. We've reached the edge of observation, the cosmic microwave background that marks the farthest light can have traveled to reach us. But does the universe end there? Does reality stop at the boundary of what we can observe? The answer, according to our best understanding of physics and cosmology, is almost certainly no. Beyond our cosmic horizon lies more universe, perhaps vastly more, but remains forever hidden from direct observation. This is the realm of the unknowable universe, where observation gives way to theory, evidence gives way to speculation, and our cosmic humility reaches its ultimate expression. Let's begin with the most straightforward possibility. The universe simply continues beyond our horizon, extending far beyond what we can see. This seems like the most natural assumption. After all, there's nothing special about our location in space. We're not at the center of the universe. We're just at the center of our own observable sphere because we can only see light that has had time to reach us. An observer in a galaxy 10 billion light years away would see their own observable universe, overlapping with ours but extending into regions we cannot see. If the universe is homogeneous and isotropic on large scales, meaning it looks roughly the same in all directions and at all locations, then what lies beyond our horizon should resemble what we observe within it. More cosmic web structure, more galaxy clusters, more filaments and voids continuing indefinitely. This raises a fascinating question. Just how much more universe is there beyond what we can see? Some cosmological models suggest the universe might be infinite in spatial extent. An infinite universe would contain literally everything possible. Somewhere out there, beyond countless cosmic horizons, there could be regions of space identical to our own observable universe, with the same arrangement of galaxies, stars, and planets. Given infinite space and a finite number of ways matter can arrange itself, repetition becomes inevitable. There could be countless Earths, countless versions of you, living out similar or different lives scattered across the infinite expanse. This isn't science fiction. It's a legitimate consequence of infinity combined with the laws of probability. But infinity is difficult to prove. We can never observe the entire universe to confirm it's infinite. Instead, cosmologists look at the geometry of space itself. Einstein's general relativity tells us that the universe can have different geometric shapes depending on its total energy density. If the universe contains exactly the critical density of matter and energy, space would be flat. Parallel lines remain parallel forever, and the universe could extend infinitely. If the density is higher, space curves back on itself like the surface of a sphere, creating a finite but unbounded universe. If density is lower, space curves negatively like a saddle and would likely be infinite. Measurements of the cosmic microwave background suggest the universe is remarkably flat, with curvature indistinguishable from zero within measurement precision. This supports either an infinite universe or one so large that its curvature is undetectable across the observable region. Either way, the universe is vastly larger than what we can see, at minimum hundreds of times larger and possibly infinite. Now, let's venture into even more speculative territory, the multiverse. Various theories in physics suggest our universe might be just one of many universes, each potentially with different physical laws, different constants of nature, different dimensionality, or different properties entirely. These hypothetical other universes would exist beyond not just our cosmic horizon, but beyond any possible observation, separated from us by more than just distance. One version of the multiverse arises from cosmic inflation, the theory that the early universe underwent an exponentially rapid expansion in its first fraction of a second. Inflation explains many observed features of our universe, including its remarkable flatness and uniformity. But according to eternal inflation theories, while inflation ended in our region of space, allowing our universe to form, it continues elsewhere, constantly spawning new bubble universes. Each bubble would be an entire universe unto itself, with its own cosmic horizon, its own laws of physics potentially, and its own history. These bubble universes would be completely causally disconnected from ours. No light, no information, no influence can pass between them. Another multiverse concept comes from quantum mechanics. The many worlds interpretation suggests that every quantum measurement causes the universe to split into multiple branches, each representing a different outcome. If this interpretation is correct, there are countless parallel universes representing every possible quantum outcome, throughout history. Somewhere in this quantum multiverse, every possible version of events has occurred. Universes where you made different choices, where history unfolded differently, where different events transpired. String theory, which attempts to unite quantum mechanics with gravity, suggests our universe might have extra spatial dimensions beyond the three we experience, curled up so small we can't detect them. In some versions of string theory, there could be other three-dimensional surfaces, called branes, existing in this higher dimensional space, effectively parallel universes floating in a higher dimensional realm. Our universe would be one brane among potentially many, each perhaps with different physics determined by how extra dimensions are curled up. Then there's the simulation hypothesis, the idea that our entire universe might be a sophisticated simulation running on some unimaginably advanced computer. If true, what lies beyond our observable universe might be nothing more than unrendered computational space, brought into existence only when observed, like a video game generating terrain as players explore. This hypothesis, while unfalsifiable, raises profound questions about the nature of reality itself. What unites all these ideas? The extended universe beyond our horizon, the infinite universe, the multiverse in its various forms, is that they may be forever unknowable through direct observation. We can theorize, we can find indirect evidence, we can construct mathematical frameworks that suggest these possibilities, but we may never be able to point a telescope and see them directly. This raises a crucial question for science. How do we study something we cannot observe? The answer lies in indirect evidence and logical consequences.